Algebra 2, 5.7, apply the fundamental theorem of algebra. The fundamental theorem of algebra is, if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. Corollary, if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. So if they're repeated, we have to count them multiple times. So, for example 1, how many solutions does the equation x to the third plus 5x squared plus 4x plus 20 equals 0 have? So we have to find the degree of our polynomial, which is the largest exponent, so 3. So this equation will have 3 solutions. Now they could be real, they could be imaginary, they could be repeated, but they're going to have 3. Okay? How many zeros does the function f of x equals x to the fourth minus 8x to the third plus 18x squared minus 27 have? And the answer is our degree again, so 4. Okay, it doesn't matter that we skipped the x squared. That'll just probably affect whether we have imaginary ones or not. Okay, so for example 3, we are going to find all zeros of f of x equals x to the fifth minus 4x to the fourth plus 4x to the third plus 10x squared minus 13x minus 14. So we are going to type in our equation into our graphing calculator. And we are going to hit graph. And there's our graph. Okay, so it looks like we have a 0 at -1, which we do. So one of our zeros is -1. And looks like one of our zeros is at 2. And it is. So we have another 0 at 2. So what we are going to do is we are going to divide the equation here by both of those and see what we're left with and see if we can factor it. So we have, I'm going to use synthetic division. We have -1. We have 1x to the fifth minus 4x to the fourth, 4x to the third, 10x squared minus 13x minus 14. So I bring down my 1. -1 times 1 is -1, then I add. -4 plus -1 is -5. -1 times -5 is +5, then I add 9. -1 times 9 is -9, add, get 1. -1 times 1 is -1, add, we get -14. -1 times -14 is a +14 and a 0. So we should get a 0 here because we do not want a remainder. So now I'm going to take my new equation here, which is a little bit shorter. I'm going to divide it by 2. So I bring down my 1. 2 times 1 is 2. I add, get -3. 2 times -3 is -6. Then I add, and I get 3. 2 times 3 is 6. Add, I get 7. 2 times 7 is 14. Negative 14 plus 14 is 0. That's what we wanted because we want no remainder. We want to make sure it is divisible. So we are left with 7, just plain old 7, a 3x, a negative 3x squared, and an x to the third. Okay, because we work our way backwards here. So now we see if we can factor this. And it doesn't look like we can factor by grouping. And it's not a perfect cube, so we are going to look at our graph again. So we have a 0 here where our graph bounces off the x-axis. And we have a 0 here where our graph goes through the x-axis. So this one's 2 and this one's negative 1. When it goes through, it only happens once, but when it bounces off, it happens twice. So we're going to take our equation here, 1, negative 3, 3, 7, and we're going to divide it by negative 1 again, because it bounced off our graph there. Okay, so negative 1 times 1 is negative 1. Add, we get negative 4. Negative 1 times negative 4 is 4. We add, we get 7. Negative 1 times 7 is negative 7. We add, we get 0. So we know it is a factor. And now if we rewrite this, we get a plain old 7, negative 4x, and 1x squared. And there's no way to factor this. So we have negative 1 happens twice, and we have 2. So we have 3 answers right now, and we need 5 total. So now we are going to use the quadratic formula to solve this. So A is 1, B equals negative 4, and C equals 7. And we remember our quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we're going to plug in x equals negative 4 is a positive 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 7 all over 2 times 1. So I'm going to bring this over here so that I have more space. Okay, so x equals 4 plus or minus the square root of negative 4 squared minus 4 times 7 times 1, which is the square root of negative 12 all over 2. 2 times 1 is 2. So then 4 plus or minus. Now there's a negative here, so we are going to have an I, and then 12 breaks into 4 and 3. The square root of 4 is 2, and we have to leave the 3 under the square root over 2, and then everything is divisible by 2 here. So we get x equals 2 plus or minus I root 3. So our zeros are negative 1, 2, and then 2 plus I root 3, and 2 minus I root 3. So these are both imaginary, and because there's a plus minus here, we get 2 answers. So now we have 1, 2, 3, 4, 5, which is how many we wanted. So we are done there. Okay, if it had said find all real zeros, we would have only had 3. But it wanted all zeros, and we know there are 5 of those. Okay, so, like we just figured out, when a factor, x minus k, of a function f is raised to an odd power, so it happens once, or 3 times, or 5 times, then the graph of f crosses the x-axis at x equals k. But when the factor x minus k of a function is raised to an even power, the graph of f bounces off the x-axis at x equals k. Okay? And just like we saw in the example there as well, complex conjugates theorem. If f is a polynomial function with real coefficients and a plus bi is an imaginary zero of f, then a minus bi is also a zero of f. So we had 2 plus I root 3 and 2 minus I root 3. So we had the positive and the negative conjugates of this imaginary zero. Okay, it also works with a rational conjugate. So suppose f is a polynomial function with rational coefficients and a and b are rational numbers such that the square root of b is irrational. If a plus the square root of b is a zero of f, then a minus the square root of b is also a zero. So if this is a zero, then its conjugate also has to be a zero. So write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and 3 and 2 plus root 5 as zeros. So how we set this up is we write it in factored form. So we're going to have x minus 3 as one of our factors, and then we're going to have x minus 2 plus root 5 as one of our zeros. And then, since we have this one, we know we have to have its conjugate. So 2 minus root 5 is another one. And we don't want to add any extra numbers or anything because we want a leading coefficient of 1. And we want to make it as simple as possible. So, if we wanted to leave it as f of x equals this, we technically could. Or we could FOIL it out. So I'm going to leave the x minus 3 the way it is right now and FOIL these first. So I get x squared first, and then outer, so I get minus 2x, minus means plus root 5x, then inner, I get negative 2x minus root 5x, because I distribute this negative. And then last, I get negative 2 times negative 2, so 4. Then negative 2 times positive root 5, so negative 2 root 5. Then negative root 5 times negative 2, so positive 2 root 5. And then negative root 5 times positive root 5, so minus the square root of 25, so 5. Okay, so this cancels with this cancels with this, and I get x minus 3 times x squared minus 4x, combining those, minus 1. Combining those, and then I distribute here, so I get x to the third minus 4x squared minus x minus 3x squared plus 12x plus 3. multiplying the x times everything, and then the negative 3 times everything over there. So now I combine terms, and I get f of x equals x to the third minus 7x squared plus 11x plus 3. And that is our polynomial of least degree with zeros 3 and 2 plus root 5. And it has a leading coefficient of 1. So we have successfully answered that question. Now, Descartes' rule of signs. Let f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus, continued, until we get to a sub 2 times x squared plus a sub 1 times x to the first plus a sub 0 be a polynomial function with real coefficients. The number of positive real zeros of f is equal to the number of changes in the sign of coefficients of f of x, or is less than this by an even number. The number of negative real zeros of f is equal to the number of changes in the sign of coefficients of f of negative x, or is less than this by an even number. So, for example 5, determine the possible number of positive real numbers, negative real numbers, and imaginary zeros for this function. So, if we count, we have a positive to a negative, so we change once. Then we have a negative to a positive, we change again. We have a positive to a negative, we change a third time, and then it stays negative the rest of the way. So we have 3 sign changes. So positive real zeros. I could either have 3, or I could be less than that by an even number. So 2 is the first even number. 2 less than 3 is 1. And if I go any lower than that, I have negative, and that doesn't make sense. So those are my number of positive real zeros. Now for negative real zeros, it gets a little trickier, because first we have to plug in negative x. So negative x to the 6th minus 2 times negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x to the 3rd minus 6 times negative x squared minus 8 times negative x minus 8. And then we have to simplify. So, even if this is a negative number, if it's raised to the 6th power, it stays positive. And then this is raised to the 5th power. So the negative is going to make it stay negative. So negative 2 times a negative x to the 5th is going to be a positive 2x to the 5th. Then raised to the 4th power, our negative goes away, so we have a positive 3x to the 4th. Raised to the 3rd power, our negative stays. So negative 10 times negative x to the 3rd is a positive 10x to the 3rd. This negative goes away, so we stay with a negative 6x squared. This negative stays, so negative times the negative is a positive 8x, and then minus 8. So we are positive. We stay positive. We change to a negative, so that's our first sign change here. And then we change back to a positive, so that's our second. Then we change back to a negative, so that's our third sign change. So again, we have 3, or a number less than that by an even number. So the first even number is 2, so we can go down by 2 and get 1. Okay, so Now, for our imaginary zeros, we can only have an even number of imaginary zeros. So, for imaginary zeros, we can have 2. Now, we're going to have a total of 6 answers here. So, we could have 2 here, 1 here, and 3 here. So, that would make 6. Or, we could have 4 imaginary, 1 positive, and 1 negative. Okay, we can't have 0 positive or 0 negative because we went down by an even number. So we can't have 6 imaginary zeros. We can only have 2 or 4 imaginary zeros. So those are our numbers of options. So now we're going to find them using these directions here at the bottom. So we're going to type in our function first, x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x to the 3rd minus 6x squared minus 8x minus 8. We're going to graph it. So we turned the calculator on, we hit y equals, we entered our function into y1, we hit graph, now I see my graph, so I don't need to change my window. So I'm going to hit second trace, so second, which is this blue button over here, and then trace, which is this button up here. I'm going to select the second one, which is 0. And I'm going to scroll using my left arrow until the cursor is left of the 0 I want to find. So I'm going to move left until I'm past this 0. And I hit enter. And then I'm going to scroll right until I'm past that 0. Hit enter. And then I try to get as close as I can. And hit enter. And at the bottom I see 0 is negative 0.732. So I get x equals negative 0.732. And then I want to find this one. So I hit second trace again. Go down to 0. And then I go over until I can see my cursor, but I still want to be left of my answer. So I don't want to go too far. So now I'm right of my answer. And then my guess will be there. And I get that my x is 2.732. 2.732. Okay, so those are the only 2 zeros I see. So that means that I must have 4 imaginary. So I had 1 positive, 1 negative, and 4 imaginary zeros here. And we just did example 6 on the previous page, being able to look at the instructions. So we are done with our notes here.